Welcome back to the deep dive. I have to be honest with you, when I first looked at the stack of papers for today, I genuinely thought there was a filing error.
Oh, because of the topics? Yeah, I can see that.
Right. I mean, I thought, surely these two things do not belong in the same sentence. We are sitting at the intersection of two buzzwords that are, well, they're usually mortal enemies.
It does feel like a total contradiction in terms, doesn't it?
Completely. We are talking about crypto mining and eco-friendly AI.
Two things famous for their tiny carbon footprints.
Exactly. I mean, usually when I hear crypto mining, I picture these massive server farms in a warehouse somewhere, burning enough coal to power a small country just, to solve Sudoku puzzles.
Right. The energy burn is legendary.
And when I think of AI lately, it's the exact same narrative.
Yeah.
Huge data centers, massive power grids, water cooling towers just steaming in the desert.
It really is the energy narrative of the decade right now. But the feasibility study we are breaking down today, it's this document titled Very Low Power AI Processing Card from February 2026. It flips that script entirely.
It really does. It takes a hard look at the energy crisis in AI and asks this incredibly provocative question.
Yeah.
What if the solution to sustainable AI is to build chips the exact same way we build Bitcoin miners?
Which I know sounds completely counterintuitive, but the document makes a really compelling case. And just to frame this for everyone listening, we aren't talking about training the next GPT-5 in a giant warehouse.
Oh, not at all.
We are talking about edge AI.
Right. The unglamorous but totally essential stuff. Smart cameras, drones, wearable tech. The devices that need to be incredibly smart but are tethered to, like, a coin cell battery or a tiny lithium pack.
Exactly. And the problem right now is that our current chips are just way too hungry. You try to run a complex vision model on a drone today, and your flight time drops from 20 minutes down to 2.
It's a total showstopper.
It is.
So the mission for this deep dive is to unpack this technical study and figure out, can we actually build a super efficient AI chip by adopting what they call a crypto mining philosophy?
And we should probably just jump straight to the spoiler alert here, because the executive summary does not hide it.
Go for it. What's the verdict?
The verdict is a resounding yes. But, and it is a massive, but it requires a major sacrifice. The study claims that if we are willing to strip away flexibility...
Meaning we stop trying to make chips that can do everything.
Right. If we do that, we can achieve efficiency gains of 10 to 100 times over what we have today.
10 to 100 times. I mean, that is not a marginal gain. That is a generational leap.
It's the difference between walking and driving a sports car. It completely changes the math.
Okay, let's unpack this crypto mining philosophy. Because to the average person, that philosophy is basically burn energy to make money.
Right. But in hardware design, it means something very specific. It refers to the evolution of the ASIC.
ASIC.
Yeah, which stands for Application-Specific Integrated Circuit.
Okay, let's break down the difference between an ASIC and, say, the chip that's in my laptop right now.
Sure. So think of the CPU in your laptop as a general contractor, like a handyman.
Handyman. It's okay.
A handyman is versatile, right? He can fix a leak, he can paint a wall, maybe build a bookshelf. But because he has to be ready to do literally any of those things at a moment's notice, he carries around a massive toolbox. He spends a ton of time switching tools, reading different manuals, figuring out what to do next.
He's flexible, but he's not terribly fast at any single task.
Exactly. And he burns a lot of energy just managing his own versatility.
That makes sense. That's the CPU. It has to run Excel, then YouTube, then Photoshop. It can't optimize for just one thing because it doesn't know what I'm going to click on next.
Precisely. Now look at a Bitcoin miner. The source specifically mentions the Bitmain Antminer S19. That machine is not a handyman.
What is it, then?
It's a factory robot on an assembly line that does exactly one thing.
It just hashes.
That's it. It runs the SHA-256 double hash algorithm. It does it billions of times a second. It cannot browse the web.
It can't run Doom?
No, it cannot play a video game. If you ask it to do literally anything else, it is a very expensive paperweight.
But because it only does that one thing, it sheds all the overhead.
Exactly. No tool switching, no figuring out instructions. Just raw, blistering execution.
And that is the aha moment in this paper. They want to apply that same ruthless specialization to AI. Instead of a chip that can run any neural network, you build a chip that runs one specific neural network.
Right. You hard code the mathematics right into the silicon. In Bitcoin, it's hashing. In AI, it's matrix multiply accumulate operations.
MACs.
Yes, MACs.
We should pause on that for a second because MSEs are basically the heartbeat of deep learning. It's essentially multiplying two grids of numbers and adding up the results.
Over and over and over again. If you look at a neural network for, say, image recognition, it's really just millions of those MSE operations happening in sequence.
So the proposal here is to log in the network topology, let's say a specific model for spotting pedestrians, and build a physical circuit that perfectly represents that exact math.
Exactly. So the electrons just flow through the gates, and the math happens automatically. You aren't wasting power asking the chip what instruction is next.
And that's where the massive efficiency comes from.
Yeah.
The metric they use to prove it in the document is TOPS per watt, right?
Yes. Trillions of operations per second to a watt.
It's kind of like the miles per gallon of the chip world.
That's a great way to put it. Speed matters, obviously. But in edge devices, efficiency is absolutely king.
Because you only have so much battery.
Exactly. And the study shows that when you eliminate that handyman overhead, the instruction decoding, the cache management, you aren't just gaining 20 or 30%. You're gaining orders of magnitude.
But getting there isn't just about doing less. The document actually outlines 4 specific technical pillars, like a secret sauce, that make this work. And honestly, this is where the engineering gets really clever.
It really is. The first pillar is something that might actually sound a bit scary to software people. They call it extreme quantization.
Quantization usually means reducing precision, right? Like making the numbers less exact.
Right. So in a standard computer, when you do math, you're usually using 32-bit or 64-bit floating point numbers. It's incredibly precise.
It's like calculating a restaurant tip down to the 10,000th of a penny.
Which is great if you're doing scientific simulations or trying to land a rover on Mars, but do we really need that level of precision just to spot a cat in a photo? That's the core argument here. Neural networks are probabilistic by nature. They're kind of fuzzy. They don't need infinite precision to know that a picture contains a cat. So the source argues for moving down to 4-bit, 2-bit, or even binary processing.
Wait, binary? Like 1 bit? Literally just ones and zeros.
Just ones and zeros. You are essentially turning complex calculus into a massive high-speed game of yes or no.
And the energy savings there must be huge.
Oh, they're massive. The source notes that just moving from 32-bit down to 4-bit or binary reduces the energy cost of the math operations by 4 to 16 times.
Because you're literally moving fewer electrons to get the same answer.
Exactly.
Okay, so pillar 1 is make the math simpler. What's pillar 2?
Pillar 2 tackles how data actually moves around the chip. They propose using something called systolic arrays.
Systolic? That sounds biological, like blood pressure.
The analogy is very intentional. In a normal chip, you have a processor and you have memory. The processor grabs a piece of data, works on it, and then puts it back.
So it's very stop-and-go traffic.
Highly inefficient, lots of idling, lots of wasted time.
Right.
A systolic array is much more like a heartbeat. The data is pumped through a grid of processing cells in a continuous rhythmic wave.
Okay.
Cell A does a calculation and passes the result immediately to cell B, which passes its result to cell C. The data just flows through the chip without constantly going back and forth to the main memory.
Oh, I see. It's like a bucket brigade. You don't walk all the way back to the well every time. You just hand the bucket to the person next to you.
That is the perfect analogy. And that leads us directly into the third pillar, which addresses the memory bottleneck.
The classic computer architecture problem.
Absolutely. The authors state this very clearly in the text. Moving data is the biggest energy sink in computing, period.
Wow.
It actually costs significantly more energy to move a byte of data from off-chip memory into the processor than it does to actually do the math once it's there.
So the commute costs more than the actual work.
Yes. So the third pillar is utilizing massive on-chip RAM.
Static random access memory. Basically, putting the storage right next to the calculator.
Inside the calculator, really. The goal here is to fit the entire AI model, all the weights, all the parameters, directly onto the chip itself. You want to eliminate traffic to external DRAM completely.
Because if you have to go off-chip to fetch data, you've already lost the efficiency game.
Exactly. You've killed the battery just making the trip.
Okay, so we have simple math, we have rhythmic data flow, and zero commute for the data. What is the fourth pillar?
The fourth pillar comes down to the manufacturing itself, just raw physics.
The physical silicon.
Right. To get the power draw down to the levels they're talking about, we're talking 0.5 or 0.8 volts, they need highly advanced process nodes. The paper specifically mentions 7-nanometer FinFET or FD-SOI technology.
Okay, so these are the tiny high-performance transistors that you'd find in flagship smartphone chips.
Exactly. You need that absolute bleeding-edge level of precision to run a chip at such low voltages reliably.
Right.
When you combine all four of those ingredients, the simple math, the fluid data, the local memory, and those tiny transistors, that is how they get to the claim of 100 times more efficiency.
I really want to ground this, though, because 100 times efficiency sounds like marketing fluff. Let's look at the actual benchmarks provided in the source. How does this compare to a standard chip I could go buy on Amazon today?
The comparison is pretty stark. The document includes this data table that pits their AI mining concept against standard edge hardware. Let's look at the Google Edge TPU first.
Which is a dedicated AI chip. It's definitely not a slouch.
No, it's a fantastic piece of engineering. The Edge TPU gets about 2 TOPS per watt.
Okay, 2 TOPS per watt.
Then there's the NVIDIA Jetson Nano, which is basically the go-to for robotics hobbyists right now. That one hovers around 0.1 TOPS per watt.
That's significantly lower.
Right. Now look at the proposal from the study. They are targeting a baseline of greater than 10 TOPS per watt.
Okay.
And for highly specialized networks where they really strip everything down to the bone, they believe they can hit 100 TOPS per watt.
So compared to the NVIDIA board, we are talking about 1,000-time improvement.
In terms of raw math per watt, yes, we're not talking about an incremental software update here. It's a completely different class of physics.
What does that actually unlock in the real world? Because numbers are abstract. If I have 100 TOPS per watt, does my toaster suddenly become sentient?
Probably not sentient, but it definitely gets eyes.
Okay.
The source gives a really concrete example here. They talk about MobileNet V2. It's a very standard computer vision model used to identify objects. Cat, dog, car, intruder.
Which is a pretty heavy workload for a battery-powered device.
Usually, yes. It'll drain a battery incredibly fast. But with this proposed chip, a device running on just 1 single watt of power could process that vision model at full resolution at 30 frames per second.
30 frames per second on 1 watt. That is basically real-time HD video analysis on a battery that could last for weeks.
Exactly. Doing that with current tech would drain a standard battery in minutes, or it would require this massive heat sink just to keep the chip from melting down.
So this tech brings true high-fidelity computer vision to things that run on button cells. That completely changes the landscape for things like smart doorbells, wildlife cameras, AR glasses.
It completely removes the power constraint that's holding those devices back.
But here we go.
There is always a catch.
If this technology is really this revolutionary, why isn't NVIDIA doing this? Why isn't every major chip maker rushing to build these right now?
The document actually calls it the elephant in the room. They call it the flexibility tax.
Which we kind of touched on with the handyman analogy earlier.
We did. But we need to look at the harsh financial reality of it. Remember the factory robot that welds the car door?
Right, the one that only does one thing.
What happens to that robot if the car design changes? What if the manufacturer decides to move a bolt 3 inches to the left?
The robot is totally useless. You have to scrap it.
That is the massive risk with ASICs. If you design a chip specifically for one exact AI model, say, a very specific version of a convolutional neural network, and then Google or OpenAI releases a new, much better architecture next month.
Your newly manufactured chip is obsolete before it even hits the shelf.
And in the AI world, next month is practically a lifetime. New models are coming out every single week. The field is moving so fast that locking yourself into hard silicon is just a massive gamble.
And it is a very expensive gamble. I mean, the source mentions NRE costs.
Right, non-recurring engineering. That's essentially the setup fee for the factory.
Pieces design it.
Exactly. The study cites it takes strictly greater than $10 million just to get to the tape-out phase.
So you have to spend $10 million just to get the blueprints ready for the factory to print.
Before you have manufactured or sold a single chip. And to make that money back, you can't just sell a few thousand units to hobbyists. You need serious volume.
What kind of volume?
The source says you need to move more than 100,000 units just to break even.
Wow. So this isn't for a niche project. You need a killer app. You need to know for a fact that 100,000 people want this exact AI model running on their specific device.
And you have to be absolutely sure that the AI model won't be totally outdated by the time the factory actually finishes building the chips.
Plus, the software side sounds like a total nightmare. I assume you can't just write some Python code and hit run, can you?
Not at all. Standard tools like PyTorch or TensorFlow, they assume you're running on a flexible GPU or CPU. For this, you need highly specialized compilers. The text mentions tools like TVM or Glow, just to map your code onto this very strange, very rigid piece of silicon. It's a huge, heavy lift for developers.
So it's high risk, high cost, high difficulty. But in exchange, you get unbeatable efficiency.
That is the fundamental trade-off.
Let's look at where this actually lands then. If a company accepts those risks, what are the applications that justify a $10 million bet?
The market landscape section of the study identifies a few really strong contenders. Smart cameras are obviously the big one. Security, wildlife monitoring, drones, basically anything where you need to process video without plugging into a wall.
I noticed audio was a big one in the paper too. They mentioned always-on keyword spotting.
Right. Think about your smart speaker at home, or even a modern TV remote. It has to listen 24/7 for a wake word. That constant listening drains power. But if you can do that keyword spotting for less than 0.1 watts, you can put voice control into almost anything. Light switches, kids' toys, kitchen appliances, and the battery would literally last for years.
And then there's wearables, AR glasses.
That's kind of the holy grail for this tech. Gaze tracking and pose estimation. If you want smart glasses that know exactly where you are looking in real time, you need cameras pointed at your eyes, processing video constantly.
Which creates a lot of heat.
Yes.
And you definitely don't want a hot processor sitting directly on your temple.
Exactly. This technology could bring that computing power into a 0.2 to 0.5 watt budget, which is cool enough to wear comfortably all day.
Now, there was one other application mentioned in the text that circles back to the very beginning of our conversation. The crypto connection. They call it distributed inference services.
Yes. This is easily the most futuristic idea in the whole paper, the AI mining concept.
Break this down for me, because it sounds like we are right back to Bitcoin again.
Structurally, yes. But the actual value proposition is totally different. So Bitcoin mining uses proof of work, right?
Right.
You are burning massive amounts of energy to solve a math problem that is fundamentally useless in the real world just to secure the network.
It's essentially a lottery.
Exactly. But imagine a very similar network where the work being done isn't random math, it's actual inference.
Actual AI tasks.
Yes. So someone in London needs a batch of medical images analyzed. Someone in Tokyo needs a huge audio file translated. They broadcast that task out to the blockchain.
And my chip, this low-power ASIC sitting on my desk, grabs the task.
It grabs the task, processes it using that ultra-efficient circuitry, sends back the result, and you get paid in tokens.
So it monetizes the hardware exactly like a crypto miner, but the output is actually useful work for society.
It turns AI processing into a global utility. Instead of Amazon or Google owning all the servers and giant data centers, the processing power is distributed across millions of people's homes.
And because your chip is 100 times more efficient than a normal GPU, your electricity bill is negligible, which means your profit margin is much higher.
Exactly.
That is a wild concept, a decentralized grid of specialized AI workers. It's almost like Uber for processing power.
It's super compelling. It completely solves the monetization problem for the person buying the chip. Even if you aren't using your smart camera right now, the chip inside it can be working for someone else and making you money.
Okay, I am sold on the potential here. But when does this actually get real? Because the source includes a roadmap.
It does, and honestly, it is a very sober reality check. This is not a Kickstarter campaign shipping next Christmas.
Give me the timeline.
The 5-year plan breaks it down pretty clearly. Phase 1, which is months 0 to 12, is just concept and algorithm co-design. You spend a full year just proving the math works on paper.
Okay, so a year of just whiteboards and simulations.
Exactly. Then months 12 to 24 are design and verification. That's building the digital blueprints, running software simulations of the hardware. Then you don't hit volume engineering until months 36 to 48. That's getting the factory tooling ready, testing the silicon yields, making sure it works.
So we are looking at 4 to 5 years from the moment they say go until mass production actually begins.
Yes, it really highlights the fundamental difference between software and hardware. Software updates can be pushed overnight. Hardware moves at the speed of supply chains and physical manufacturing.
So if this feasibility study is dated 2026, we are realistically looking at 2030 or 2031 before these things potentially flood the consumer market.
Very likely, yes. And that assumes they find a foundry partner who is actually willing to take the $10 million risk in the first place.
It is definitely a long game. So let's pull all of this together. We started with what seemed like a total contradiction: crypto mining and eco-friendly AI. What is the grand synthesis here?
I think the synthesis is that we absolutely can solve the AI energy crisis. We can have incredibly smart devices that run for months on a tiny battery, but we can only do it if we stop asking our chips to be generalist handymen.
We have to accept the flexibility tax.
We do. We have to return to the idea of doing one thing perfectly. It's a massive pendulum swing back to specialized, inflexible hardware.
Which leads me to a fascinating final thought for you to ponder. If this roadmap actually succeeds, we are going to fill the world with millions, maybe billions, of chips that can only run one specific AI model.
That is the part that really sticks with me.
Right, because if we flood the market with chips that are permanently hard-coded for the AI algorithms of 2026, what happens in 2030 when the software is completely evolved?
That is the real danger here. Do we end up with a world full of frozen brains?
Frozen brains.
Yeah, smart devices that are permanently stuck in the past because their intelligence is literally etched into stone.
You could end up with a landfill of smart cameras that can only recognize the cats of a decade ago, totally unable to process new data.
It's a very real possibility. We might solve the energy crisis, but inadvertently create a legacy hardware crisis. We could be completely surrounded by dumb, smart devices that can never learn anything new.
That is a haunting thought to leave on. Next time you look at your smart device, you've got to ask yourself, is it a generalist burning power to be flexible? Or is it a specialist, frozen in time?
Thanks for listening.
We'll catch you on the next deep dive.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.